high-frequency generator. It produces voltages up to 50,000 volts. These high voltages will produce a very strong electric field that can ionize atoms and molecules in a gas. Here is a wire mesh. Let's apply this high voltage about an inch away from the surface of the wire mesh. You can see that light is produced when we do this. That is from the ionization of the molecules in the air. Here is a fluorescent tube. Let's apply the high voltage to the fluorescent tube. You can see that light is emitted by the tube. The atoms and molecules in the tube have been ionized by the high electric field. Now, let's put the tube inside the wire mesh. And we will apply the high electric field. We see light emitted between the tip of the instrument and the wire mesh, but no light is emitted by the tube itself. The tube has been shielded by the wire mesh. This is called electrostatic shielding. These effects are seen more clearly in the dark. Here is voltage applied to the wire mesh. Now voltage is applied to the tube, and it lights up. Next, the tube is put inside the wire mesh. Voltage is applied, but the tube does not emit any light. This is a Faraday cage. It consists of a cardboard frame surrounded on three sides by wire mesh. The front side, the back side, and the left side are covered with wire mesh, and the top is also covered with wire mesh. The right side has an opening, so instruments can be inserted into it. Over here is a Van de Graaff generator. When you turn it on, the dome of the generator becomes negatively charged. And here is a piece of Teflon tape attached to a PVC pipe. I can charge the Teflon tape by rubbing it with fur, like this. When I do this, the Teflon tape becomes negatively charged. Now I will turn on the Van de Graaff generator, and we will see what effect it has on the Teflon tape. The Teflon tape is repelled by the Van de Graaff generator. We expect that because they are both negatively charged. Now let's put the Teflon tape into the Faraday cage. The Teflon tape is no longer repelled by the Van de Graaff generator. When it is inside the Faraday cage, it is shielded from the electric field of the Van de Graaff generator. Let's take it out and just verify that it is still negatively charged. It is still repelled by the Van de Graaff generator. It is still negatively charged. The electric field from the Van de Graaff generator does not get inside the Faraday cage, and so the Teflon tape is no longer repelled. I will now explain how electrostatic shielding happens. The electric field inside a conductor is zero, even when the conductor is in an external field. That is electrostatic shielding. Here's a conductor, and let's put the conductor in an external electric field. As shown here, the electric field is going from the left side to the right side. There are free electrons inside the conductor, which will move because of this external field. And in this example, they are moving from the right side to the left side. And that leaves behind positive charges on the right side. Now these positive and negative charges set up their own electric field, called the induced field. And that electric field points from the positive to the negative charges, or from the right to the left. As shown here, it is opposite to the direction of the external electric field. The net electric field, E internal, is a vector sum of E external and E induced. Since they are in opposite directions, they sum to 0. So E internal is 0. If it was not 0, more free electrons would move until it was 0. Now let's look what happens when there is a cavity inside the conductor. There's a conductor, and here's a cavity inside the conductor. The electric field inside the cavity is 0, even when the conductor is in an external field. So here's our external field, as before, going from left to right. There are free charges in the conductor which will move because of this external field as before. In this example, they move from left to right, from right to left. And they set up an induced electric field going from the right to the left, from the positive charges to the negative charges, as shown here. The net electric field inside the conductor and the cavity is E internal, which is the vector sum of E external and E induced. And they are in opposite directions, and they add to 0. So we have 0 inside the conductor and also 0 inside the cavity. When the fluorescent tube was inside the wire mesh, it was inside a cavity in a conductor. When the Teflon tape was inside the Faraday cage, it was inside a cavity in a conductor. And we observed that the electric field inside that cavity was 0.
I have now put the Van de Graaff generator inside the Faraday cage. I want to see what will happen to the Teflon tape when I turn on the Van de Graaff generator. In this configuration, the Faraday cage is not grounded, it is floating. But this metal ball is connected to the faucet, and if I touch the metal ball to the Faraday cage, like this, the Faraday cage becomes grounded. Grounded, not grounded. I also want to see what effect the grounding will have on the Teflon tape. I will first charge the Teflon tape by rubbing it with the fur. Now I will turn on the Van de Graaff generator. The Teflon tape is repelled by the Van de Graaff generator. The Faraday cage is not blocking the electric field of the Van de Graaff generator. Now let's see the effect of grounding. When I ground the Faraday cage, the Teflon tape is no longer repelled. In fact, it is attracted. Let's try that again. Not grounded, repelled. Grounded, not repelled. Repelled,
grounded, attractive.
I will now explain our experimental findings. Let's model the Van de Graaff generator as a sphere of radius r1 and charge negative q. So there's the sphere, it has a radius r1 and a charge negative q. There is an electric field in the region of space around the generator that points towards the generator, as shown here. Electric fields point towards negative charges. Now let's put that charge inside the Faraday cage. To simplify the analysis, we will model the Faraday cage as a conducting spherical shell. That will allow us to use Gauss's law, which will simplify everything. So there's the conducting spherical shell. It has an inner radius r2 and an outer radius r3. Oh, look who's joined us. It's Giselle the Gazelle. Please give Giselle a round of applause. Thank you very much. Giselle, I think I know the answer to this question, but why have you joined us at this point in the presentation? That's what I thought, because you really love Gauss's law. Why do you love Gauss's law so much? Oh, yeah. Oh, she loves the symmetry that you use in Gauss's law. You're right, Giselle. We have the symmetry here of the conducting spherical shell. We have radial symmetry in this problem. So it's a great chance to use symmetry. Oh, what's that? Oh, yeah, Giselle also loves integration. So Gauss's law uses integration, but she doesn't like solving integrals. And in Gauss's law, it is very easy to solve the integrals, as we will see. So let's continue. Let's apply Gauss's law to our model of the Van de Graaff generator inside the Faraday cage. We're going to first look at the region between the Van de Graaff generator and the inner surface of the spherical shell, between R1 and R2. There's Gauss's law. We have this integral of E.dA, and this circle means that we take it over an entire surface. And the surface we're considering is shown here by the red dashed line. That is a spherical shell of radius r. The circle means we take the integral over that entire spherical shell, the entire closed surface. E is the electric field, and we show it pointing away from the surface, and it is perpendicular to the surface. dA is an element of area, and it is also perpendicular to the surface and points away from the surface. If the electric field turned out to be negative, then we would know that it points in the opposite direction. It would point towards the charge negative q at the center. Qn is a charge inside the Gaussian surface. In our example, the charge inside this red dashed line is negative q. So Qn equals negative q. Now let's look at that integral. The integral of E.dA. Now E and dA are parallel to each other. So in the dot product, E.dA, it is just E times dA times cos 0 degrees, which is 1. So it's just E times dA. So we get the integral of E times dA. Now, because of the spherical symmetry, R is constant on our Gaussian surface. So E has the same magnitude all over the Gaussian surface. So E can be taken out of the integral, as shown here. So we get E times the integral of dA. And the integral of dA is just the surface area of the sphere of radius r. So we get E times 4 pi r squared. Now let's combine these two findings. E times 4 pi r squared for the integral, and Qn equals negative Q. We get this. E times 4 pi r squared equals negative Q over epsilon 0. Solving for E, we get E equals negative Q over 4 pi epsilon 0 r squared. That is what we would expect if the negative Q was a point charge located at the origin and we applied Coulomb's law. Now let's look at the charge on the spherical shell. The spherical shell is originally uncharged, but charge may be distributed between the inner and outer surfaces of the shell. So let's say we have a charge Qi on the inner surface and a charge of Qo on the outer surface, and we want to find these two charges. Let's apply Gauss's law within the spherical shell between R2 and R3. So here is our Gaussian surface shown by the dashed red line. It is a spherical shell of radius r. Here's Gauss's law. The integral of E.dA over that Gaussian surface equals Qn over epsilon 0. Here's an important fact. There is no electric field inside the conducting spherical shell. Under electrostatic conditions, the electric field in a conductor is 0. If it wasn't 0, charges would move until it was 0. So the left side of this equation, this integral, is just going to be 0 because E is 0 throughout. And the charge inside is negative Q plus Qi. So we have negative Q plus Qi over epsilon 0 equals 0. The result is Qi equals Q. Now let's find the charge on the outer surface, Qo. The total charge of the spherical shell is 0. So therefore Q, the charge on the inner surface, plus Qo, the charge on the outer surface, equals 0. Solving for Qo, we get Qo equals negative Q. Now that we know the charges on the spherical shell, let's apply Gauss's law to the region where R is greater than R3, outside the Faraday cage. Here's our Gaussian surface, a spherical shell of radius r. Here's Gauss's law, the integral of E.dA. Again, E is perpendicular to the Gaussian surface, pointing away from the surface. dA is also perpendicular to the Gaussian surface and points away from the surface. Qn is a charge inside the Gaussian surface. So Qn is the charge negative Q of the Van de Graaff generator plus the charge Q on the inner surface plus the charge negative Q on the outer surface, and that is negative Q. So Qn is negative Q. Let's do this integral of E.dA. As before, E and D are parallel. So it just becomes E times dA. E is constant on that Gaussian surface, so we take it out of the integral. So it's E times the integral of dA, which is E times 4 pi r squared. Let's combine the two, E 4 pi r squared and the Qn. We get this. E 4 pi r squared equals negative Q over epsilon 0, and solving for E we get negative Q over 4 pi epsilon 0 r squared. It is the same as it was inside the Faraday cage. In this configuration, with the Faraday cage not grounded, the electric field outside is the same as it was inside. Let's look at the electric field inside and outside for the floating spherical shell, which means the ungrounded spherical shell. Between R1 and R2, inside the Faraday cage, we found that E was negative Q over 4 pi epsilon 0 R squared. It points inwards towards the Van de Graaff generator as shown here. Between R2 and R3, inside the conducting spherical shell, E is 0. It's always 0 in a conductor, under electrostatic conditions. And now, for R greater than R3, outside the Faraday cage, E is negative Q over 4 pi epsilon 0 R squared. It also points inwards towards the Van de Graaff generator, as shown here. So there is no change from inside the Faraday cage to outside the Faraday cage. We still have an electric field outside the Faraday cage. The Faraday cage does not affect the electric field if the cage is not grounded. Now we want to look at the case where the cage is grounded. First, we need to understand how the surfaces become charged. As we saw, there's a charge Q on the inner surface and a charge negative Q on the outer surface. How do these charges arise? Well, if we have a positive charge on the inner surface, the inner surface must have lost electrons, because a positive charge is really the absence of an electron. So electrons must have moved from the inner surface to the outer surface, leaving a negative charge on the outer surface. Now let's consider what happens when the Faraday cage is grounded. As before, we have a charge Q on the inner surface. That cannot change, because the electric field inside the spherical shell has to be 0. And that can only happen if the total charge inside, negative Q plus Q, is equal to 0. But the charge on the outer surface may change. So I've written here Q0 equals question mark. To get these positive charges on the inner surface, they must have lost electrons. But these electrons don't go to the outer surface, they go into the ground. So the outer surface has a charge of 0. The outer surface is uncharged. Now that we know the charge in the outer surface, let's find the electric field outside of the Faraday cage when it is grounded. Let's apply Gauss's law. For R greater than R3, we draw our Gaussian surface, a spherical shell of radius r, and we have the electric field E perpendicular to the Gaussian surface, the element of area dA also perpendicular to the Gaussian surface, and both point away from the Gaussian surface. Here's Gauss's law. The integral of E.dA equals Qn over epsilon 0. Let's look at Qn. Qn is the sum of all the charges inside our Gaussian surface. They are negative Q, the charge of the Van de Graaff generator, plus Q, the charge on the inner surface, plus 0, the charge on the outer surface. So it's negative Q plus Q, which is 0. The right side of this equation is 0. The only way for that to happen is if the electric field is 0 everywhere outside the Faraday cage. So E equals 0. Let's look at the electric field inside and outside when we have a grounded spherical shell. Between R1 and R2, E is negative Q over 4 pi epsilon 0 R squared. As shown here, it points towards the Van de Graaff generator. Inside the spherical shell, between R2 and R3, E is 0. It's always 0 in a conductor. under electrostatic conditions. And now, for R greater than R3, outside of the Faraday cage, E is also 0. So the electric field is blocked by a grounded Faraday cage. So when the Faraday cage was ungrounded, the negatively charged Teflon tape was repelled, as we saw in our experiment. And when we grounded the Faraday cage, it was not repelled, but sometimes it was attracted. Why is that happening? Why was it sometimes attracted? Remember, a charged object will polarize an uncharged object, and then it will experience an attraction. So when the Teflon tape was attracted to the grounded Faraday cage, the Teflon tape must have polarized the Faraday cage, causing it to be attracted to the Faraday cage. More information on this concept can be found in my video, The Ball and Van de Graaff Generator. I will put a link in the description below. Here is a summary of electrostatic shielding. The electric field inside a conductor is 0, even when the conductor is in an external field. The electric field is 0 inside a cavity in a conductor, even when the conductor is in an external field. When we put the fluorescent bulb inside the wire mesh, we were putting it inside a cavity in a conductor. When we put the Teflon tape inside the Faraday cage, we were putting it inside the cavity of a conductor. And the electric field from outside was not able to get inside that conductor. Placing a charged object inside a Faraday cage can block the electric field of the charged object from penetrating into the region outside of the cage, only if the cage is grounded. If the cage is not grounded, the electric field from inside is able to go into the region outside. But when it is grounded, the electric field is blocked. Thank you for staying to the very end of this presentation. Giselle and I are very grateful to have you come to our presentations, and we thank you for that. Please be sure to like and subscribe, and leave a comment in the space below. See you next time.